So this lesson starts a new segment on the topic of integers. And integers are, vocabulary down here, I wrote them out up at the top. Integers are, if we want to define it this way, all, text box please, there we go, all positive and negative whole numbers. So we looked at the history of numbers and how our Hindu-Arabic number system developed. And if we look at more primitive societies, they didn't have the need for any numbers other than whole numbers. And really, until you got to a positional system of numeration, you really only had needs for the counting numbers, right? You didn't need a zero if you were working with an additive number system. So you only needed numbers 1, 2, 3, and so on. You know, if you're primitive enough where all you're doing are, you know, multiplying to find how many rows of corn you have, or, you know, you're doing some basic trading with your neighbors and you need to quantify things that way, you don't have a lot of need for numbers outside of the whole numbers. But as soon as we introduce operations, and this is where we get into this idea of closure. So we did have this definition already. I usually test on this definition at the final because it pops up a lot throughout the course, and we don't really finish talking about it until the end of the course. But anyway, this idea of closure of a set under an operation. And so a set is closed under an operation if the operation can be performed on any, so keyword is any, not just one or two numbers, but all numbers, and the result is also in the set. So if I define addition and multiplication, I don't multiply my way out of this set, I don't add my way out of this set, right? Because if I add or multiply any two whole numbers, I get another whole number. But as soon as I define subtraction, it has to work on any two numbers, right? So, well, 4 minus 2, that wouldn't be a problem, but any numbers in any order, all right? So as soon as I define subtraction, I have now subtracted my way out of this set. That means as soon as I have the operation subtraction, I need a new set of numbers. All right, and so that set of numbers is the set of integers. So integers are closed for addition, subtraction, multiplication, not division. Of course, we can't divide integers in every possible case without getting outside of our set. And so therefore, later we're going to talk about what's called rational numbers. Rational numbers includes fractions, repeating or terminating decimals, right? And we have to go into this set of rational numbers because we're going to divide our way out of the integers. But anyway, a few definitions that you need to know. So absolute value, that's going to be a term that's going to pop up here a few times for us. So that is the distance between a number and 0. All right, so that's why absolute value 4 and absolute value -4 have the same value. All right, and then the additive inverse, you know, if I asked you what's the additive inverse of, oh, I didn't mean to do that. What's the additive inverse of 10? Right, see now if we were in class, you'd all respond to me. I'd say, what's the additive inverse of 10? Right, and then someone would say -10. Right, and I'd say, what's the additive inverse of 20? Right, and someone would say -20. What's the additive inverse of -5? Someone would say 5. So you would probably call the additive inverse, you know, if I said, well, how would you define it? You would say the opposite. That's a grade school level explanation, maybe even a high school level explanation or definition. Let's give the college level definition of additive inverse. So the additive inverse of a quantity that we'll call A is the solution to x plus A equals 0. All right, that's a higher level definition. And we're actually going to use this definition to prove something really important later in the lesson. So one of the things that I teach all of my future teachers is that lessons need to go from concrete to abstract. Abstract is when we're using the rules and we're using equations. All right, concrete is when we're either using models, right? We're actually using like base 10 blocks or the chips that we're going to get to. Or concrete is when we're doing problems, like word problems that appeal to their common sense. And when I taught integers in 7th grade, I didn't teach them a single rule about integers. I gave them my very first activity in my integers lesson was I gave them a whole page of word problems. And so all of the story problems that are on this page were the types of problems that I had as my very first introduction to integers. And I just let common sense dictate. And I was a little bit surprised how well their common sense dictated their answers and their understanding. They had no rules, right? No formal lesson on this, and yet they were able to get a surprising number of the questions correct just based on their intuition and what they already know mathematically. So if we want to add, and again, we know this, right? Positive plus a positive is a positive. But if we want to add a negative and a negative, right? So I always talked about this situation where, you know, if two people come together, so remember, a marriage is a union of two people. That was my language support back for union of sets. We talked about the union as the coming together of two people. As marriage is often described. So if we add two negatives, if both people bring debt to the situation, then I result in more debt, right? A greater amount of debt. Now, going down here, even young kids can understand this idea of like debits and credits, okay? So if I have, so my story problem involved like -8 plus 10. So if I talk about this as credits and debits, right? I have a credit of 10, I have a debit of 8, right? Young kids have this, already have this notion that, yeah, you would have a positive amount of money in the end, right? You would have +2. So if I made a column over here for results. Okay, this would be +2. But if I had a debt of 12 and then I got a paycheck for 9, right, and I described it in this way, I would have a credit of 9 but a debt of 12, right? I'm still in debt and my result is -3. So the next thing that I'm going to have you do is go to, because it's talking about here models with R&B chips. I'm using the term red and blue chips. I noticed on the videos they kept on using, so when it's talking about R&B chips, they kept on using yellow, right? Why don't I circle that in yellow? All right, so they had yellow and red chips. Red is the universal color for debt, okay? So if I say, you know, this business is in the red, that's not good. All right, so whether we use blue or black for positive or yellow, red chip signifies debt. So instead of me trying to draw them out here, I went to YouTube and selected a few videos where operations with integers are being modeled. So please go on and watch that YouTube video before you pick back up with my videos. Thank you.